between S and T, so this will not affect about the 95% of the confidence interval. And after that, as we saw in the last page, we applied this for more than one type of distributions and more than one value of n. We applied this for a binomial distribution, but with 1,000 trial, and check how many samples we have to check if it's approximately 95% or not. And this is the figure. We calculate the mean. It's approximately 95% of the 1,000 trial, included the population means. Any questions?
Yes, Ahmed, I have a question about the N. So is it a good idea to choose N very large in the first case with Z here?
You know, we work with simulations, so you are free to choose any size of n, and of course, if it's increased, that means your sample will be close to the population, and that's better. But in the real life, it will make you pay more because you know the sample. If it's real, you need.
Because you will reduce the interval, the length of the interval, so this is a good thing, right?
Yeah, but as I told you, it's the 95% will still, if it's increase or decrease, as you see here, and I think you did the same. Look here, it's up. This is n small, but almost of the samples, it's approximately 95%.
So it doesn't affect.
Yes, because as I explained here, the relationship between x bar and n and the population mean, it's complex and make the percentage still with 95%. Because well, n increase, that means this guy will be decreased, but in the same time, this will be closer than population mean. So the population mean will still inside the confidence interval in 95% of our samples.
For distribution, if the distribution not normal, like for geometry, it's a fact on the interval because when I see the schedule.
Yeah, as you know, this is a random sample. When you apply this more than one time, maybe it's just stochastic to see the 918 in your sample. Maybe if you simulate a normal distribution with a high n more than one time, you will get a value similar of this.
So, sorry.
Yeah.
We learned earlier today in the class that when you have a small n and you don't know the sigma, the true standard deviation, you have to sample it.
Yeah.
You can only calculate the confidence interval if you know that the distribution is normal. So for some of those, like the geometric and uniform, if n is less than 30 and we don't know what sigma is, then that type of hypothesis testing might not be applicable. Did you come across anything that would be like a substitute or something that we could do in those cases for like the geometric n equals 15 or 3 that would increase our
With all of this distribution, you know this distribution for the random sample, but we work with x bar, the estimator of the mu, and the x bar with this limit center theorem distribute with normal distribution with mu and sigma over n. Yeah.
The central limit theorem only applies if n is greater than 30. So for n is 3 and 15, we can't make that assumption. So I was just wondering if there were other methods for the extreme cases.
Look, there is a confused too. I will go to this to the figure to explain to you where is n, because we have number of trial and we have a sample size. And that's make our distribution go to normal distribution is the number of trial here, not the number of size. Because how many X bar you have? You have 1,000 X bar. That means X bar go to the normal distribution. But the size that you calculate X bar from it is 3 or 5 or 15 or any value. Yeah.
So that is the right question. No? N is the size of your sample, and when your size of sample is small, then you should justify. Then the CLT does not stand. For such cases, you can do bootstrap. But the number of trials is not the sample size. The sample size is your N. And that was the reason that they gave you small N's for that, while the number of trials were.
But how many X bars we have to? Like when we say X bar, when we say X bar has a normal distribution. X bar, there is a 1,000 X bar and has a sigma X bar. And this is sigma X bar related to how many trials, how many simulate the sample.
The CLT tells you that your underlying estimate has a normal distribution when your sample size, N is your sample size, right? Not number of trials. But that is why you see that controversial thing that you have for geometric.
Yeah.
For a small n, then you are not meeting the supposedly confidence interval, right?
Okay.
And you can compensate for that using the bootstrap method. Yeah. But yeah, that could be the confusion. The n for CLT is the sample size, is not the trial numbers. The sample size is the size of your sample. So when it's n3, it means that CLT